Okay, so we have a midterm exam on Wednesday, November 18th. So just wanted to kind of cover topics that that'll be tested, and it'll be a similar format. I think this one will just kind of be all pen and paper. This is my current plan. This is what I've planned. Okay, so timed exam, 1 hour plus 10 minutes for scanning and submitting. All right, so exam is open note, open book. You can consult Wikipedia or the R help files. No discussion on Campus Wire, and you're not allowed to talk to each other. And then, just like last time, you log in with Zoom with your cameras on. And then I'll have I got exams scheduled for 10 a.m. or 10 p.m. California time. So you don't need to tell me when you're going to take it. Just show up and take it, okay? And you'll submit your kind of this pen and paper portions by scanning them and submitting them via Gradescope. So yeah, you'll have 1 hour and 10 minutes, 1 hour for the exam, 10 minutes for scanning and submitting, okay? And then, if you're planning to take it at 10 p.m., don't open the 10 a.m. file. And if you take it at 10 a.m., don't open the 10 p.m. file. Okay. All right. So this is kind of what I've written down. So number one is going to be, you're going to do random number generation with convolutions. So I'm going to provide kind of a sample of random values. Like I might give you like 4 random uniform numbers. And then, and you'll turn those numbers into like values from a binomial distribution, or you'll turn them into values from a chi-squared distribution or gamma distribution or something like that, okay? So you'll apply some kind of convolution and things like that. Some of the convolutions might require exponential values, and you'll have to use inverse CDF to do that. And then, with that, you should be able to produce values from either, binomial, chi-squared, T, gamma, or beta distributions, okay? And that should be that, okay? Does that make sense? Any questions there? Okay, so, you'll probably get a few parts on this, okay? Problem 2 will be rejection sampling. Okay, I'm going to provide some kind of arbitrary target distribution. Okay, I'll provide like the PDF of a target distribution, and then I'll also provide an arbitrary proposal distribution. So, and so based on that, you'll need to find. Sorry. Okay, you need to find the optimal M. Okay, might require, and that'll probably require a bit of calculus or thinking about the functions that I've provided here. Okay, so I'm not going to try to be like super mean about it, but be prepared for a little bit of kind of math work there. All right, regarding finding where the max is, because you're gonna have to find the max of f of x over g of x. So you'll have to figure out where the max is and figure out what that value is for m. Okay, and then and once you have that, then I'm going to provide some random values generated by the proposal distribution. I'll say, this value came from the proposal distribution, and each value I provide will be paired with a random u, okay? And based on that, you'll find the acceptance ratio, and you'll tell me if this proposed value should be accepted as part of the resulting sample or not. Okay, I hope that makes sense as well. And then parts 3 and 4 are Metropolis Algorithm, the discrete case, and continuous case. And this is where you have homework currently assigned. And I think if you do your homework and you pay attention to what's happening, don't just focus on writing the code, but also think about how the thing works, I think that will be helpful in preparing for the exam. Okay, so I'm going to provide an arbitrary target probability mass function. Okay, so it's going to be discrete, discrete distribution, and then I'll also specify instructions regarding how new states will be randomly proposed. So it's a discrete case. The new states, just to introduce something a little bit different, it's not going to be exactly the same as the politician visiting the islands, right? So right now the politician visits the islands or proposes a value by flipping a coin, and if it's heads, he goes to the right. If it's tails, he goes to the left. And there'll be some kind of instructions like that, except it'll be a little bit different. Okay, so small modification from how the new states are randomly proposed. Okay, but given that, you'll be able to find the transition matrix. I'm going to ask you to find the transition matrix P. Okay, so that'll be basically a K by K square matrix for across the K possible states. And then given the distribution at some time t, it'll be a distribution over the K different states. I'm going to ask you to find the distribution at time t plus 1. Okay. Maybe t plus 1 and t plus 2 or something, right? And for that, it's basically multiplication and stuff, and you can use R for some of the calculation stuff. So you're allowed to use R to assist with your calculations. Obviously, you'll want to show some work for at least what the operation is that you're doing, and then as far as like doing the actual multiplication and stuff, you can kind of print that out. Does that kind of make sense with what's happening here for problem 3? Okay, and then the last one is the Metropolis algorithm, but the continuous case. And for this one, I'm going to provide a continuous arbitrary target PDF distribution. Okay, PDF. So I'll provide that function. And then I'll provide a proposal distribution. And I'll tell you right now, the proposal distribution will either be a uniform distribution going from x at time t minus a to x at time t plus a, or the proposal will be x at time t with an arbitrary sigma. Okay, and I'll provide some arbitrary starting location x at time t, and I'm going to ask you to perform 2 or 3 iterations of the Metropolis algorithm manually. All right, and for each of those, I will provide random U1 and U2 values that you're going to use in your calculations. Okay, these are both going to be from the uniform distribution, and then you use U1 and inverse CDF. So you got to use inverse CDF of either this uniform distribution or this normal distribution to find the proposed value of x. Okay, so make sure you understand how that works, right? So given your current location, if I give you, a random u, where's the proposed value going to be? Okay, and you can use R, or you'll probably have to use R for some of these inverse CDF calculations, especially if it's inverse, if it's the normal distribution. Okay, and then you'll have to find the P move, that acceptance probability, and you'll use U2, the other uniform value, to decide whether the new chain will move or not according to the Metropolis algorithm. And then, and based on that, you'll report the next value of x in the chain. Okay, and that's it. That's going to be kind of what you can expect for the second midterm. Again, my recommendation is do the homework that's been assigned, especially for these Metropolis algorithm ones. So you've already done homework, so hopefully you feel familiar with problems 1 and 2, and then this the homework that's being assigned now should get you familiar with problems 3 and 4. And again, focus on, you know, if it wasn't written in code, and if you had to do this kind of manually in the calculations, like, can you do it, right? Like understand how the values are being proposed and things like that. All right, is that good? Okay, so this this document has been posted to CCLE, and I think that's that. Okay, then let me, so for today's lecture, I was going to go over the Metropolis Hastings algorithm, which is maybe a slightly more general version of the Metropolis algorithm. And then I will kind of work through, I guess, a small kind of, I don't know, proof or whatever that that the stationary distribution of the Metropolis Hastings algorithm will be the target distribution. Okay, and so so today's notes will all be kind of, I guess, whiteboard work here, where I don't have slides prepared here. Okay, so so today we're covering the Metropolis Hastings algorithm. Okay, and this is a generalization of the Metropolis algorithm. Okay, so in the Metropolis algorithm, the proposal distribution g of x needs to be symmetric. Okay. Okay, that is to say that if you're currently located located at x of t, the probability of proposing x prime is going to be the same value as proposing xt if you're located at x prime. Okay. Probability of proposing x prime if you are currently at xt is equal to the probability of proposing xt if you are currently at x prime, right? So like, for example, the normal distribution so the probability, these two values are equal. If you're at xt, proposing x prime is going to be equal to if you're at x prime proposing xt, right? So those probabilities are equal. So because it's symmetric. Okay. Metropolis Hastings relaxes that algorithm, or that requirement. Does not require these two values to be equal. Okay. All right, and pretty much the so the algorithm remains almost the same, and it's just the kind of that acceptance probability of kind of whether we move or not. Just takes that into account. Okay, so I'm going to just kind of the Metropolis Hastings algorithm. Okay, number one, pick an initial state. X0. Okay, and then number two, iterate. Okay, and step A, I guess 2A will be generate or propose. Propose a candidate. X prime, which comes from G of X prime given. Okay, propose a candidate based on the current value xt. So this part's exactly the same. Okay, and then calculate kind of the acceptance probability. Which we've been calling p move. And that's going to be the minimum between 1 and probability of x okay times g of okay, and technically you can also use some f that is proportional to p. Okay, so p of x is the target probability. So right here is the target distribution. Okay, and you can also use f of x proportional to p of x, right? So you have the target probability distribution, and if you don't have the actual target probability distribution, p of x, you can use a an f of x that is proportional to it. Right. Okay, and then 2c will be accept or reject. Okay, generate u from our from uniform, and then if u is less than p move, accept x at time t plus 1 is x prime. And if u is greater than p move, reject x at time t plus 1. is the current value x at time t. Okay, and then repeat. All right, that's the Metropolis Hastings algorithm. So the only thing that changed between this and the Metropolis algorithm is that now we have this kind of factor that it takes into account whether g of x t, so for the Metropolis algorithm, this part is just equal to 1, right? For the Metropolis algorithm, this part's just equal to 1, so it's not that big of a deal, and it just becomes probability of x proposed divided by x current, right? The probability of the proposed location divided by the probability of the current location. That's going to be kind of your acceptance probability. In the Metropolis Hastings algorithm, we take into account that, perhaps proposing a new location is harder or easier depending on, where you are. Okay, is that all right? Metropolis Hastings algorithm, very similar, just a small tweak here that allows for things to be different. Okay, so I guess I could draw a picture here or something. All right, so I wanted to show why it works. Okay, so I'm going to show that the Metropolis Hastings algorithm works, and then you can then use the same logic and say the Metropolis algorithm works in the same way. It's just that, g of x prime given g of x at your current value, is equal to the other. Okay, so the Metropolis Hastings algorithm works because it satisfies what we call detailed balance. Detailed balance at the stationary distribution. Which is to say that if you've got state x at time t and x at time, let's just say x prime here, is that the amount going from x at time xt to going to x prime, these two are exactly equal. Okay, so the amount flowing from is exactly equal to kind of the opposite flow. Okay, and this will be true for any two states. I should say this will be true for any two states if the states follow the target probabilities P of x. This will be true for any two states if all the states follow the target distribution. P of x. Okay, so So a couple things. All right. So P of X will be the probability of being at state X probability of being in state X, okay, at the target distribution. Okay, and then probability of this, it will be the probability of transitioning from state xt to x prime. Okay, and so what we need to show, and I guess I'll do this on the next slide. Show that probability of xt multiplied is equal to that. Okay, so that this is kind of the flow from xt to x prime. So this will be kind of the amount flowing from xt is equal to amount flowing in the opposite direction. Okay. And this, I guess this would be the kind of the probability of starting at xt at state xt multiplied by kind of the transition probability of transitioning to x prime. Okay, and then this would just kind of be the opposite, right? Probability of starting at x prime multiplied by the probability of transitioning to xt. Okay, so there's technically a trivial case. Okay, and that is if the proposed location is rejected. Okay, so this happens in the Metropolis and Metropolis Hastings algorithm is if the proposed location is rejected, then x, the next location, x prime becomes xt, right? The next state, we'll just say x prime becomes x at time t. Okay, and then therefore, you know, if you plug in, if everything just becomes xt, then the two sides are going to be equal to each other. If the proposed location is rejected, the next state x prime is equal to xt, and both sides of the equation are equal. So that's kind of the trivial case. But what we want to do is we want to show this thing is true for two different states, okay? So I'm going to just copy this. This is what we will do on the next slide here. All right. Okay. So far, so good. Everybody, I forgot to give you your quiz answers. Let me give you your first two. First two quiz answers for today are A and C. Apple and cat. A and C for the first two quiz answers for today's lecture viewing quiz. A and C, apple and cat. All right, so this is what we want to show for, other than the trivial case. Okay, so over here, what I've got is I've got probability of x at time t. Okay, and this thing, okay, I guess I'll copy it down, okay, of x prime given xt. This part becomes, first we have to propose g of x prime given that we're at xt. So this, I guess I'll start on the left-hand side. So I'm going to just copy this down. Probability of xt multiplied by we have to propose it, and then we'll multiply it by the acceptance probability, which is going to be the minimum of 1. And we look at the target divided by, so the target of the proposed divided by the target of the current times, and then we kind of have this this business here, xt given x prime. So again, so I'm doing this for the Metropolis Hastings algorithm, but you could do it for the Metropolis algorithm, and this part will just be replaced with a 1, and you'll see that the same logic applies. All right, is this okay? So all I've done is that this thing, the transition probability is the equal to the value being proposed multiplied by its acceptance probability. And the acceptance probability is the min of 1 and this thing. Okay, so what I'm going to do is I'm going to replace the 1 here with p of xt over p of xt, okay? So maybe I'll just kind of jot this. So I replace 1 with p of xt divided by p of xt. Okay, and so now I got probability. Oh, and then and I will also distribute g of I replace this, and then I also distribute this through the minimum, okay? G of x prime given xt through the min function. Okay. So I'm distributing g of x prime xt through the min function, okay? And I'm replacing 1 with p of xt over p of xt. Okay, so I've got p of xt multiplied by the minimum of p of xt divided by p of xt. Okay, so the 1 gets replaced with p of xt over p of xt, and I'm going to multiply by g of x prime given xt. Okay, so that's what I have on that side, comma, and then over here I've got p of x prime divided by p of xt multiplied by g of xt given x prime. And then technically the g of x prime, I guess I'll go ahead and put it here. G of x prime given xt will cancel with the g of x prime given xt. And so this will cancel with that. Okay. And then now I'll distribute the p of xt. Through the minimum function. Okay, and so this p of xt basically will cancel with this and will cancel with that. Okay, so this will, I don't know how to show this. Okay, but all right. So on the left-hand side, I've got the minimum of p of xt multiplied by g of x prime given xt, and p of x prime times g of xt given x prime. Is that okay? All right, and then I can do the other side. How do I do this? Will this fit? Okay. I'll try to fit it on this side. Okay, but it's the same logic, and we're going to end up with the same thing. Okay, we're going to end up with the same thing down here. All right, so I've got so I'm going to kind of split this up. So I'm going to have to write a little bit smaller. So I've got p of x prime. So on the right-hand side, I've got p of x prime multiplied by g of xt given x prime, okay, times the minimum of 1 and, so it's probability of proposing. So now we're going from x prime to xt. So it's going to be the probability of going to xt given that we're currently at x prime times g of x prime given that we're at xt divided by g of xt given that we're at x prime. Okay, and again, I'm going to distribute this throughout the thing. So I'm going to have probability of x. So kind of using the same logic here. I'm going to have the minimum between, and then I'm going to have p of x prime over p of x prime times, and I'm distributing this. I've got g of xt given x prime. So the minimum of that, and then on this side, I've got probability of xt. Oops. It's on the bottom, xt given or divided by probability of x prime times g of, if it's okay, I'm going to just go straight to the canceling here, given xt. Okay, so this will, you know, this part will cancel, gets distribute, right? So distribute this. And then this will be replaced with probability of x prime divided by probability of x prime. Okay, and then, and now I'm going to distribute this. Okay, and so on this side, I'm going to get, this side is equal to the minimum of probability of x prime times g of xt given x prime, and probability of xt times g of x prime given xt. Okay, and what we see is that these two things are exactly equal. They are the same. Okay, so the amount flowing from this side from xt to x prime is going to be the minimum of whatever this product and this product are. And the amount flowing the other way from x prime to xt is going to be the minimum between this value and this value. And so, so whatever it is, the two things are going to be equal to each other. All right. And that's that. Okay. So, you know, and if you think about kind of the island hopping example, and so I think in our class example, you know, let's say we have island 2 and island 3, and island 3 is a bigger island than island 2. Okay. So what is the amount flowing from island 2 to island 3? Okay. Well, whenever island 3 gets proposed, that is g of x prime over xt. So whenever island 3 gets proposed, you know, we're going to take whatever amount is in island 2, and it's going to 100% of it flows from island 2 to island 3 because island 3 is bigger. And then, but what about going in the opposite direction? The amount going from the opposite direction from x3 back to x2 is basically, you know, we take a ratio between the smaller island divided by the probability of the bigger island. And, you know, and after it cancels out, it just becomes a probability of kind of the, you know, the smaller island multiplied by, you know, kind of proposal value. So they end up being the same. Okay. So anyway, this is just to show that these two things are equal, meaning that we have detailed balance, that the amount flowing from one state to the other is equal to the amount flowing from that state back to this state. And that's that. Okay, let me give you your last quiz answer for the viewing quiz. Last quiz answer for the viewing quiz is D. D as in dog. D as in dog. Okay, I don't know if we had any questions. I hope the steps I did here were okay. I'm trying to show detailed balance here. And that's kind of how this all works. All right, so next week, I've got I think a pretty neat application of the Metropolis algorithm. So we'll take a look at that. And I've given you the stuff that you need to study for the midterm exam on Wednesday. So hopefully that should be all set and good to go. But yeah, and then next week I'll introduce we'll do a neat little application of it. Okay, that's it. That's all I got for you guys today. So we'll end a few minutes early. Have a good weekend, and we'll see you Monday.